Okay, today we're going to start looking at the Standard Model and fundamental particles. To begin with, I'm going to give you a brief history of the exploration of subatomic physics. So, to begin with, let's look at how our understanding of the atom has changed over time. So, back in the 5th century BC, Democritus proposed that matter could be cut into ever smaller particles. But he proposed that there would be a point where you couldn't cut that. So he said, say you got a slice of bread and you have to have a slice of bread, then you have to again and have to again, and kept halving it. And you'd go smaller and smaller, and he had this thought experiment that you get smaller and smaller and smaller and smaller bits until you came to a point where you couldn't cut it anymore. And he called that small piece that was uncuttable an atomos. And that is where we get our word for atom. Sadly for Democritus, his idea didn't really take off, and it wasn't till centuries later that people began to take his thoughts seriously. In 1808, John Dalton, an English physicist, he began to do scientific experiments into the nature of atoms. And up until that time, it wasn't really possible to do those type of experiments. The technology wasn't there to probe the structure of the atom. And his discoveries led to confirmation that Democritus was pretty much right. That things are made up of these small particles. We'll come to later that an atom is not the smallest particle that we can get, but when you go into pull the atom apart, you come down to these tiny little particles. So John Dalton proposed that every matter consists of atoms, and they're like little billiard balls, and these billiard balls join together to make compounds. And that was Dalton's contribution into the history of the atomic model. It wasn't until 1904 that we moved forward from this. But again, there was the limitations of technology, and J Thompson discovered the electron. And he knew the electron was a small, negatively charged particle, and he proposed the plum pudding model. So he thought it was a bit like a plum pudding, where you've got your cakey puddingy bit, but there would be these little negatively charged particles in the same way that you get currents in a plum pudding that would just be found dotted throughout the atom. So these wee bits here are the electrons that are negatively charged, but he thought that they were sitting inside this positively charged puddingy bit. This was the first time that it was shown that an atom was not indivisible, that the atom itself was made up of something that was, they said it was positively charged, and these electrons that were negatively charged particles. Therefore, the atom wasn't the smallest particle that we could get. Then in 1911, you'll notice now that the time between discoveries is getting shorter as technology advances. In 1911, Rutherford conducted a really famous experiment called the gold foil experiment. He fired some alpha particles at a thin sheet of gold foil, and he expected them to fly right through it, and they didn't. They dispersed, and they went off in different directions. Some bounced right back and were detected coming right back off the gold foil. And from that, Rutherford deduced that the atom wasn't like this solid ball. It had a positively charged nucleus, and the electrons were kind of floating around the positively charged nucleus, and that the majority of the atom was in fact free space. In 1913, Niels Bohr gave us the Bohr Model, where you have the positively charged nucleus, but now the electrons are orbiting the nucleus. In the 1920s, this model was refined by quantum mechanics. So we get the quantum mechanical model, which is a bit beyond what we're going to be doing just now when we're looking at the subatomic particles, but later on when we do some quantum physics, this is going to come into play. So I'm just going to put it in here for completeness. So Schrödinger proposed that you have the positively charged nucleus, but these electrons, you can't really know where they're not just kind of sitting in these, spinning around in these nicely defined orbits. They kind of whiz about, almost like an angry kind of irritable fly. However, so these would be the orbitals. Each orbital takes on a distinctive shape. If you were to watch the video of this electron and track its course, you'd find some would make a spherical shape, some would make kind of more these kind of elliptical kind of shapes. And that's because in the quantum mechanical model, we can't know the position of a subatomic particle precisely. It's all to do with probabilities, and there's a probability of that electron being in a particular point. However, what comes out of both the Bohr model and the quantum model is that we find that electrons are taking on distinct energy levels, that there's only distinct and specific amount of energies that these electrons can take as they orbit the nucleus. So although the quantum mechanical model is the more accurate model that we currently have, we can simplify it down to the Bohr model for a simpler, more easy to handle way of thinking about the atom. So when we think about the electrons, we're thinking about them orbiting the nucleus. They're taking on these distinct levels which refer to the energy that these electrons have. They can't just have any energy, and that's going to become something that we'll be looking more into when we look at waves and spectrum, and how the electromagnetic spectrum and how light and how different and all of that, how that works, that comes out of the atomic model and the way that electrons take on these distinct energy levels. Now, whilst this was going on, they were also probing the nucleus and what the nucleus was made of. So they knew the electrons are negative, and they knew the nucleus was positive because the overall charge of the atom was, unless you've got an ion, but the overall charge of the atom was essentially neutral. So once they started to probe the positively charged nucleus, they knew it must be made of something that was positively charged. In 1999, Rutherford, who gave us this model of the nucleus, he discovered protons. Then in 1931, so quite a wee bit afterwards, neutrons were discovered. And those were discovered by Chadwick. The thing that made them harder to detect was because they're neutral, so you can't see their effects with through their charges. And it was discovered by probing the masses of atoms and seeing that actually the number of protons in an atom only accounts for about half the mass of the nucleus. So there must be something else there adding to the mass, and that's where the neutron came from, and it was proven to exist by Chadwick. So that is where we're going to come into this to look more closely at the nucleus. So we're going to be probing the nucleus in more detail. How we probed the nucleus, we fired alpha particles or beta particles or gamma rays. At a nucleus, and that by doing so we destabilize the nucleus, and we cause the state of that nucleus to decay, and the quantum states within that nucleus to change. And by firing different types of radiation, we can then detect what is the result of those collisions, and that gives us an idea of what's going on inside the nucleus and what the nucleus is made of. So firstly, when we fire alpha particles at the nucleus, what we find is the particles that are emitted have the same kinetic energy as each other. So each alpha particle that's emitted after these collisions, each particle that's emitted after we fire alpha particles at the nucleus, all the resultant particles have the same kinetic energy, and that kinetic energy is dependent on the type of isotope that we're firing these alpha particles into. And this makes sense. This is confirmed. It's the expectation that the quantum state transition, so the energy that is at the beginning, before the collision, is going to be the same as the energy after. You're going to have that conservation of energy, that the particles at the beginning, all their kinetic energy added together is going to equal the kinetic energy at the end, that the energy of these particles is going to be the same. Conservation of energy. What was then interesting is what happened when they fired beta particles. So when they fired beta particles at the nucleus, they discovered something very, very interesting. This is the curve, the relative frequency curve of the energies of the particles that are emitted from a collision of a beta particle and an atom. And you can see that these beta particles are taking on different energies. And there's this energy range. And that was a bit of a problem. If the nucleus undergoes the same quantum state change each time the beta particle is emitted, then what happens to the missing energy? You're not seeing this conservation of energy. There's missing energy from these particles. So why do some particles appear to have more energy? So these ones here have more energy than these ones down here. Why is that? And that was the problem which physicists had. So in 1930s, an Austrian physicist named Pauli proposed that there was another particle being released during these collisions. This particle had to have very small mass. In fact, almost no mass at all, and no charge. In the group of physicists that Pauli was working with was another physicist called Fermi, and he proposed to name this new particle the neutrino. When the collision occurred, there'd be beta particles that would have these high masses, and there'd be other beta particles released, and they'd have these different masses. And this gap, this missing energy, would be made up by the energies of these neutrinos being released. You're going to see that during the development of the Standard Model, many of the things that were proposed have come out of maths, and the looking at these theories and different ideas through the lens of maths would lead to the hypothesis of various different particles existing, and it wouldn't be till later when the technology caught up that these particles would be discovered and the theory would be verified. So this was the solution to this missing energy. Now, at the same time as this was happening, there was an English physicist named Dirac, was looking at the solutions to equations with square roots. So if you, just for example, say you had x squared equals 4, you know that x must equal plus and minus 2. That in mathematics that makes perfect sense, but in the real world that can lead to some difficulties having negative square roots. And he discovered that when he was doing these equations and he was getting negative square roots, that this had the consequence of leading to a new type of matter. And he called this matter antimatter. So again, we see how maths has led to the discovery of a whole new area of physics. So it was proposed that antimatter particles have all the same characteristics same characteristics as matter, but opposite charges. So, for example, you have the electron is matter and it's negatively charged, and its antimatter counterpart is a positron, which has the same mass as an electron and other properties of the electron, but has a positive charge. Now, matter and antimatter, they annihilate each other. And the energy released is Einstein's famous equation E equals mc squared. So when you get a matter-antimatter particle coming together, they annihilate each other, and the energy produced is that all their mass is turned into pure energy, and that's how you would calculate their energy. Now, it turns out when you have a really high energy density, you're able to reverse the process of annihilation and actually produce a matter and antimatter pair. And that's been done in particle accelerators. Now, back to our problem with this curve and our missing energy. The energy that this neutrino that was, I'll bring this back up. So the neutrino being emitted has to be an antimatter anti-electron neutrino. So it's a type of neutrino that's associated with electrons, and it's an anti-electron neutrino. And they worked this out from some very complex maths, and from looking at the quantum mechanical theory behind it, and that's what they came out with. And again, this has now been verified through 25 years after they actually proposed this. They were able to prove it by the use of particle accelerators. They needed a lot of very high energy particle accelerators to be able to do this. So, now, what we're finding, the structure of our nucleus is starting to look quite complicated. What we thought was just protons and neutrons is beginning to appear that there's much more happening at a fundamental level than what we first thought. In the 1960s, American physicist Gell-Mann proposed a model of nucleons. So a nucleon is a neutron and a proton, the thing that the nucleus is made of. He proposed a theory of nucleons that they were actually composite particles. They weren't fundamental particles at all, that just they could be cut up even smaller than what they already were. And he proposed that nucleons were composite particles made from fundamental particles, or as far as we know, fundamental particles called quarks. Interestingly, the word quark comes from a word made up by the novelist James Joyce to describe the noise a seagull makes. Where Gell-Mann thought to associate the noise of a seagull to this fundamental particle, I do not know. So Gell-Mann called the quarks that make up a proton and a neutron up and down. So this is our proton, and you have an up quark, an up quark, and a down quark, and they are held together by forces which we'll find out later are strong forces. The force is called the strong force. And here is our neutron, and that's an up quark, a down quark, and a down quark. Gell-Mann went further than just saying that protons and neutrons were made up of these quarks joined together, the ups and the downs. He proposed that there were three families of quarks, or generations, you can call them families or generations, and they increase in mass in each generation, and therefore they increase in energy because the mass is related to how much energy they have. In the current low energy conditions of the universe, we only see ups and downs in existence. The other quarks are very short-lived. You can make them in particle accelerators, but they quickly disappear. But these up and down quarks can make these stable arrangements that form protons and neutrons. With each generation of quark, there is associated with it a much lighter charged particle and a neutrino pair. So these pairs are known as leptons, which is the Greek word for light. And let's have a wee look at what this looks like. So this is what we call the standard model of particle physics. So we have our quarks. The first generation is up and down, and then we have the associated charged particle, which is our leptons. So we have our electron and our neutrino electron. So this is our first generation, and this is what we are familiar with. Our up and down quarks make our protons and our neutrons, and we have our electrons that are in our atoms, and the associated neutrino is the neutrino electron. The second generation of quarks are called charm and strange, and they have leptons. The leptons associated with charm and strange are the muon and the muon neutrino. Then we have a top quark and a bottom quark, and they have leptons associated by a tau and a tau neutrino. We've already touched on the matter and antimatters, the mirror. So we have for every one of our quarks and leptons, we have an antimatter equivalent. So we have an anti-up and anti-down. And if you see, we have this little line above the symbol for each particle, and that just denotes that this is the antimatter equivalent of our matter particle. Later on, you'll discover that there are other forces that are responsible for the interactions of forces that keep all these different particles in place, and all the different fundamental forces have different particles, and that's what we have here. But we won't, not to worry about these just now. But these types of particles are called bosons, and you have a gluon. A photon is one that we'll speak about in more length later, and then there's Z, W, and W plus and W minus bosons. The photon, so if you were to think of electromagnetism, for example, when you have electromagnetic interactions, photons are released, and photons are they are the particles that kind of carry, and they allow other particles to know that that particle kind of is there, if that makes sense. If you want to think about in our, when we drew our proton, we had our up. Oh, that's terrible. Let's get rid of that. Down. So to hold these quarks in place, they feel a force that keeps them together, and we denote that with that little squiggly line. And along this are these little particles that kind of interact to say that these quarks exist, that they're here, and that they feel that force. So forces are this interaction between different particles, and those interactions have fundamental particles associated with them. So if that makes sense. Now, when you combine quarks together, so combinations of quarks are called hadrons. So there's other particles that have been made in particle accelerators with different combinations of these quarks. And when you get a particle made up of quarks, it's called a hadron, which is the Greek word for heavy. Pairs of quarks, so if you get two quarks together, these particles are called mesons. A triplet is called a baryon. So a proton and a neutron would be a baryon. The electrical charge of the resultant particle must be an integer number. So if you see, you can't really see here. I can draw on that. So the up has a positive charge of 2/3. Down has a positive charge of, not a negative charge, sorry, of -1/3. Charm has positive 2/3. Strange -1/3. And a muon, notice a muon is a top has 2/3 and a bottom -1/3. So when you add these together, when you're building your particle, these charges have to add up to be an integer. So if you add up the up, down, you will get an integer number of, for our proton, +1. And for a neutron, the charges cancel out to be 0. You can't get a fractional quantity of charge. Now, because of this, because the electrical charge must be an integer number, mesons, are made up of mesons are a matter antimatter pair. and therefore are very short-lived. They annihilate. For example, the meson group of pions are made up of up and down quarks, and their lifespans are, so pions is a family of mesons, and their lifetimes are between 10 to the minus 16 and 10 to the minus 8 seconds. Baryons can be made up of either 3 matter quarks or 3 antimatter quarks, and they are stable combinations because they don't have that mixing of antimatter and matter, and that's why we are a matter universe and not a combination of matter and antimatter, because we would just be annihilated. The standard model has been verified through experiment by looking for these particles in particle accelerators, and it's regarded as a triumph for theoretical and mathematical physics, because it was all proposed from the mathematics and later verified by the experimental. We're going to go on to discuss more deeply how these particles interact and the forces between them, and that will then take us on to look at the gluon, photon and the bosons to see how this all works together.